Hi everyone, welcome to the COMP2521 Revision Session. My name is Eric and this is Andrew, and we'll be going through the main topics for this course. First of all, I'm going to start with the binary search tree. So as everyone should know already, binary search trees are the data structure that is associated with the binary search algorithm, which is an algorithm, popular algorithm associated with the divide and conquer paradigm. Yeah. First, let's go through the components of a binary search tree. So, of course, to enforce the algorithm for binary search, each node must have at most 2 children, right? And the 2 children that are subnodes of a main node, so for example, let's say 87, the 2 nodes must be either smaller or greater than the parent node. And specifically, the node on the left must be smaller and the node on the right must be greater. And obviously, as enforced by the name binary search, binary meaning 2, there must only be 2 nodes for each parent node. Yeah. And also, let's go through some general terminology for binary search trees. So, the solitary node at the very top level of the tree is called the root node. You can, the name makes a bit more sense if you visualize the binary search tree more as an upside down tree. So as you know, the bottom of the tree consists of the tree's roots, where all the branches branch out from. Similarly, if we visualize the binary search tree as an upside down tree, the singular node at the very top is called the root node, and all other nodes branch out from it. And yes, these are the leaf nodes. So leaf nodes are any nodes that have no more children nodes. So that means, just like in a tree, right? For example, any branch of a tree basically stops at the leaf, right? The leaf is the tail of the branch. So yeah, these are the leaf nodes and they have no more nodes attached to them afterwards. Yeah. Now, we also have subtrees. So subtrees are just a graph whose vertices and edges form a subset of the given tree. So if we kind of view the given tree as like a set, right? Then a subtree is basically just a subset of the given tree. And yeah, so it's just a collection of subnodes. So for example, when we relate to the right subtree of 51, it's just a tree that is taken when we take 87 as the root node. So basically the tree that branches out from the node 87, which is the children of 51, which is the child of 51. Yeah. And similarly, this will be considered the left subtree of 51. So that's the right subtree and that's the left subtree. Yeah, and okay, I kind of used this terminology before, but the children, like the child nodes, are just nodes that are, just the nodes that 51 is connected to. So the nodes that are levels before this 51 node. And consequently, the 51 node is known to be the parent node, as the 2 children nodes originate from the parent node. Okay. Now let's actually dig into the software implementation of the binary search tree. So here we've got some C code. Struct node represents a node in the binary search tree. And within the struct node, we have a value, a left, and a right. Obviously, each node in the tree must hold some sort of data, right? So this data can be abstracted away as the int value. And similarly, we have a left node, so which is the node on the left of it, right? Can anyone tell me any properties that this left node must hold for it to be appropriate? Alright, so because of binary search, this left node must be smaller than the parent node. So yeah, this left node must be smaller than value. So the value associated with the left node must be smaller. And similarly, the value associated with the right node must be greater than the value. So that binary search works. So yeah. Oh, we got that again. Sometimes you may see another field in the struct. So you might see the field int balance or something, right? Which I'll cover later on with AVL trees, because for AVL trees it's important to keep track of the height of your subtrees. But generally, a binary search tree just usually looks like this. Yep. Now let's go through the traversal of the tree. So this is actually, I think, a pretty confusing topic, because it's really hard to actually visualize in your head how all this traversal works. So there's 4 types of traversals. There's pre-order traversal, in-order traversal, post-order traversal, and level-order traversal. Now, I'm not actually too sure how much traversal is used in 2521 exams, but I know that later on there's a few lead code mediums that might require some combination of these orders to do the question. So yeah, it's pretty important information to know about. And yeah, all of these are O-event operation, because obviously to explore all the nodes of a tree, you have to visit each node, right? And there are n nodes in the tree, so of course, consequently, the time complexity must be O of n, as you have to explore each node. Let's start with pre-order traversal then. So as the name suggests, pre-order traversal consists of visiting the node prior to traversing the left or right subtree. So if we look at the code here, okay, printing the node basically just means visiting the node. So yeah, we print the value of the node before we recursively call the traversal operation on the left node and the right node. And yeah, and the order that this produces will be shown on the next slide. Yeah, so for example, if we had this binary search tree, the first node that would be visited would be 32, because as you remember before, from the code, the node is visited before we explore the left or right subnodes. So yeah, so 32 will be explored first, and then 16, and then 4, and then 1, and then on the next slide. Yeah, so this is the general order that that would be motivated by the pre-order traversal. So we start with 32, and then we go on to 16, and then we go on to 4, and then we go on to 1. I think, yeah, so you could try to actually understand how this works by digging into the traversal. So if you look at the code, right, because we visit the node prior to visiting the subnodes, that's why we, when we start from 32, we visit 32 first. And then we visit 16, and then 4, and then 1, and then 5, right? But then if we compare it to the other orders, so on the next slide, when we look at something like, oh yeah, that's pre-order traversal. So yeah, on the bottom, it shows the order that all the nodes are visited in. So 32, 16, 4, 1, and then 5, and then 20 and 22. Yeah, I think to memorize this, you could basically just memorize this big line. So you can kind of think of pre-order traversal as if you were trying to draw an outline of the binary search tree, and the general order would basically be like this, right? And yeah, so the next slide. And then next we have the in-order traversal. Once again, as the name suggests, we visit the node in between the traversal of the left and the right node. So yeah, we visit the node in between, and due to this order, obviously, this will produce a different traversal combination. So next slide. Yeah, so once again, if we start with the same tree, the order is a bit different. So you can kind of think of in-order traversal as if you are exploring the tree from left to right. So for example here, right? We start with 1, and then we go to 4, and then we go to 5, and then we go to 16, 20, 22, 32, 35, 37, 39, 41. And yeah, as you can see, I'm simply just exploring the tree from left to right, right? And that's, I guess, kind of an easy way to think about in-order traversal. And once again, you can also just look at the code really hard and think and visualize the recursion calls happening in your head. But yeah, if you're like pushed for exams and stuff, maybe just memorize that, it goes from left to right. But I think the best way to do it would be just really try to visualize the stack recursion in your head about how all this works. Do you guys have any questions about like this traversal stuff? Alright, next one. Now we have post-order traversal. So this is what happens when you visit the node after you recursively call the traversal on the left and right subnodes. So yeah, as you can see in this code, we traverse the left node first and the right node first, and then we finally do the visiting. Next slide. And next slide as well, yeah. So now let's see the consequences of this type of traversal, right? So it's actually, I would say it's kind of similar to in-order traversal. So my analogy before with in-order traversal was that you explore the nodes from the left to right, kind of. But now it's kind of like from right to left, except you go by the subtree. So for example, right, we start with 1, and then we go from 5 to 4, and then we go from 22 to 20 to 16, and then we go from 35, and then 39, 37, 44, 50, 45, 41, 32, right? It's kind of like from right to left. But yeah, once again, it's a bit weird. So I recommend you to actually just go through the code and visualize the recursion in your head. I could go through it, but I think everyone visualizes it differently. It's really abstract, and I think that's the main difficulty with COMP2521, and also later on if you were to dive into lead code and all the DSA stuff. So yeah, that's post-order traversal. Yeah. And finally, we have level order traversal. So the implementation of level order traversal is a bit different. Generally, it would involve some sort of keeping track of the level of the tree that you're in. And yeah, if you're curious, I could go through like how the code for level order traversal works. I'm pretty sure it's like a lead code problem as well. But yeah, so as the name suggests, you traverse the nodes of the tree by the level. So you start from 32, and then we do 16, 41, 420, 37, 45, and so on. So that's in order. That's level order traversal. Yeah. So yeah, those were the four types of traversals. Although I guess like the actual point of level order, like all these types of traversals isn't exactly like obvious, but I think later on it's useful if you were to, I don't know, just explore the trees in weird ways. Yeah. Okay, now let's look at height in the binary search tree, because obviously, obviously the main benefit of a binary search tree is that it enforces binary search. And as you all know, compared to linear search, which is when you iterate through all of the elements of a list one by one and find the node you're looking for, binary search basically, it's a divide conquer. So it divides the problem, right, into a smaller problem, and then it basically keeps dividing the problem into smaller problems until we solve it in the end. And by dividing it into a smaller problem, obviously it's easier to solve a smaller problem than a bigger problem. So yeah, that's the main, that's basically what binary search is like from a really high level. And yeah, so we have 4 main operations for a binary search tree. We have insertion. Obviously you want to add more data to the existing database that you have. We also want to delete in case we want to delete anything. And we also want to search, which is the main crux of binary search. Right. Yeah, so let's go through a bit of code. So binary search, this is a code for binary search. It's pretty simple because just like binary search, like binary search upon a sorted array, if we were trying to search for a value, we basically just iterate through each level of the binary search tree. So we start from the root node of the binary search tree. We start from the root node, and if the value that we're trying to find is smaller than the root node, then we continue on to search to the left subnode of the root node. And vice versa, if the value that we're trying to find is greater, then we continue to search on to the right subnode. And since this is recursion, right? It's basically we just take the left subnode of the root node and pretend that to be the root node, and then we just keep searching. And yeah, and because of this divides the problem into smaller subproblems by going through each level and then basically decreasing the size of the space that we're trying to look for. So yeah, that's how binary search works with a tree. And similarly, we also have binary insert. So yeah, BST insert. BST insert is basically similar to binary search, right? So we still have a target node. And what we do is we go through the binaries. We first search for where the target should be in the binary search tree, right? So as you can see, all this is basically the same as that. And then once we find where the target is, then we create a node at the top, and then that joins the tree together. Although I think the code for insertion is a bit weird, because it's kind of weird how you can insert through recursion, right? Because recursion through exploring, I think it's pretty self-explanatory. It's easy to visualize, but I think it's pretty hard to visualize how the insertion works. But basically what happens here is you have to kind of think of insertion as relinking the tree together, right? So if we have a node n, we basically just relink the node n with its left subnode. And similarly, we relink the node n with the right subnode. And then we just keep doing this until we find a spot where we need to insert a node, right? But initially there's nothing there, right? Obviously when we're trying to insert something there was nothing there to begin with. So what we do is we keep relinking, and then at the very end when there's nothing there, we put the node that we want to insert in that place, and then we relink it, right? So, and that's how insertion works. I think that's the best way I can explain it. So we just keep relinking the binary search tree until we find where we need to put the node, and then we link the node together, and then the binary search tree is completed. So yeah, so that's insertion. Do you guys have any questions for the software implementation of all these operations? All right, yeah. So yeah, in each iteration we are progressing down one level of the tree. And yeah, and if you think about a binary search tree, right? The number of levels there are in the tree is approximately log n, where n is the amount of nodes in the tree. And you can also calculate this mathematically, right? So, it's like log base 2 n or something, because because it's binary, so there are two subnodes for each node. Next one. Yeah, so the time complexities of all these operations, I'm not going to go through BST joy, but it's pretty simple. You just take all of the nodes of another tree and insert it into the first tree. But we have insertion, which has complexity of OH. Same with deletion as well as search, right? Because, to be honest, all three of these are basically the same thing. Because it all involves searching for the place where you're trying to do the operation first, which is OH, and then doing the operation, which is O(1). Now, the problem with a normal binary search tree is that while the time complexity of OH, right, which is usually log n, let's say, for example, that the tree was imbalanced. Let's say that we have a tree, right, that's just something like this. So only one of the subnodes is used, right? So if we have a node 0, and the right node is 1, and the right subnode is 2, and the right subnode is whatever, right? This is basically like a linked list. And as you know, with searching through a linked list, the searching operation for a linked list is O of n, and not O of log n. And the implications of this is drastic, right? Because as you know, with log n, as n increases, log n actually, the rate of increase of log n as n increases decreases. However, if we have an operation of O of n, it's like a really big difference, right? We can look at a graph as well. Like, you know how like log n looks like this, right? But n looks like that, like it just goes towards infinity like really, really fast. So yeah, it's a really big difference. And when your software scales, it makes a pretty huge difference with log of n and O of n. But yeah, so this is the main problem with binary search trees, because if the tree were somehow to be imbalanced, then all our search and all our deletion would be in a time complexity of O of n, which is exactly what we don't want. Because the main point of binary search is to benefit of the fact that you can do everything in log of n, which is really fast. Yeah, but however, if we were to have a very well balanced tree, then even the worst case time complexity would still be O of log n. Whereas with a rudimentary tree with with a naive implementation, the worst case time complexity would be O of n. So that's why AVL trees exists. So as you guys know from assignment 1, AVL trees are binary search trees that self-balance. As in, when you insert or delete nodes or do anything to the tree, the state of the tree after your operation is always balanced. And because it is balanced, the worst case time complexity for all of its operations are O of log n, which is really good. Because, that's the whole point of a binary search tree, to do everything in log of n, which is really fast. But there is one crucial property of LVR trees, because, and it's represented by this equation here. The height of the left subtree minus the height of the right subtree, when we take the absolute value of that, it must be smaller or equal to 1. So basically, it's just saying, like, the tree must be kind of balanced, Like when a tree is balanced, it basically just means the left subtree and the right subtree is like approximately the same size, and that's what this equation tries to represent. And if we ever insert a node to the binary search tree, to the AVL tree, that breaks this rule, then that's where the crucial part of the AVL tree comes in, which is where we have to write an algorithm that rebalances the tree whenever an imbalance happens. And we do this through rotations. And the really good thing about AVL trees is that insertion and deletion, like the actual inserting and the deleting part, is still O of 1. So that's really good. So it's constant time, the actual insert and the actual deletion. And the O of log n just comes from searching for the place to insert or delete. And yeah, the memory, is still O of 1. So AVL trees are basically perfect in the sense of binary search trees. So the main concept with AVL trees is that we have to do a bunch of rotations to achieve the balance that we want. And these rotations basically consists of a child node taking the position of its parent node, right? And this kind of makes sense. Like, let's say you had a parent node. Wait, next slide. Maybe there's like some picture for it. Yeah, for example, here, right? Like, okay, there isn't really like an imbalance here, but it's kind of like this part is a bit bigger than this part. So we want to redistribute all these nodes, right? And really the way we do that is we just we take the parent and then we swap the parent down to the child level, and then we get the child and we swap to the parent level. So that's kind of what rotations are. I'm going to go back. Yeah, and yes, and yeah, basically all of these rotations, like the software implementation, what we do is we take a child node, and then we swap the positions of the root node and the child node, right? And then we rearrange the links so that the primary search tree or the ABL tree is linked up again. And yeah, that's how all these rotations work. And there are two types of rotations. There are left rotations and right rotations. And with a combination of at most two of these rotations, the ABL tree can be imbalanced. And because there can only be at most two of these rotations that will be necessarily performed, because of that, the insertion and deletion are all constant time, right? Because 2 is the greatest amount of rotations that we need to do. So yeah, that's why ABL trees are really good. Next one. So let's first start with a right rotation. Yeah, look at that. Yeah, so let's say we want to rotate this to the right? Okay, it's probably better to think of it more like clockwise, because like I'm kind of stupid. It's like if I think about twisting it to the right, it's kind of hard to think about right? So I think we should more think about like clockwise, and the direction makes a bit more sense. It's like turning a key, right? If we like turn this, as you can see, 32 goes towards the right, and then 16, basically the subtree of 30, the left subtree of 32 goes up, and 32, as well as the right subtree, goes down, and this happens. But obviously that's not a binary search tree, right? There's like 3 child nodes there. So what we then do is we rearrange this middle link, and then we put it down here. And then it becomes like that. And yeah, so for example, with the right rotation, right? I'm not gonna go through the code because there's like a lot of stuff for it. But basically, the right rotation rotates it to the right while still maintaining the property of binary search trees, in that the left node is always smaller than the middle node, and the right node is always greater than the middle node. If you guys want to, I could go through like some formal mathematical proof of how this actually works by taking in bounds like alpha, beta, and whatever. But since this is a revision session, I'm just gonna go through like the rote learning strategies, like the best way to do it as fast as possible. So yeah. Yeah. So now let's also do a left rotation. So yeah, so it's an anti-clockwise twist. The child node 15 takes the place of the parent node 10. And then we move the 12 down here. Next slide. And the result is that we have 15 up there, 10, 14, 12, and 17. And yeah, so that was the left rotation and the right rotation. And however, sometimes when we're inserting stuff, it might take a combination of left and right rotations. And next slide. Yeah, so these are the different combinations. So let's say that if we have a node with an imbalance called n, and we wanted to well, I can talk about that later actually. Yeah, but these are the 4 combinations that we have. So we have we can either do a rotate right once, or sometimes there's situations where you have to combine 2 rotations at a time. So rotate left as well as the rotate right. And yeah, so these are the 4 combinations. And in the software, so I'm pretty sure you will be given a pseudocode of how it works. I remember being able to take in notes to COMP2521 or something. So that's why I'm not exactly placing too much emphasis on the software implementation, because you can simply take those notes in. But I am gonna actually focus on the general high-level concept of how all this works. So yeah, these are the 4 types of rotations. And now let's actually go through an example of one of these types of rotations. So here we have a really big tree. Is this tree balanced or no? Is it not balanced? Actually, I used to think this was imbalanced, because low-key it looks kind of imbalanced, right? Why is this part so fat and then why is this part so little, right? But by the general definition of AVL trees, this tree is actually balanced, because with a AVL tree, all it has to, all the property that it has to conform to is that the left subtree, the difference between the height of the left subtree and the right subtree can be at most 1, right? And if you go through every single part of this AVL tree, even though this part is a bit discombobulated, that there's nothing there, it's still balanced, because if we go through all of the heights, it still conforms to the property. So yeah, but yeah, this one. Yeah, so this tree is balanced. However, if we were to insert a new node 18 here, right, then this tree becomes imbalanced. And let's go through the tree level by level actually, and let's find where the imbalance is. So let's first start with 29. So can anyone tell me what the height of the left subtree of 29 is? Alright, it's 5. So if we start from that level, 15, and then that level, so 1, 2, 3, 4, 5, right? So the left subtree height is 5, and the right subtree height is 1, 2, 3, 3. 5 minus 3 is 2. So obviously, there's an imbalance there. There's an imbalance between the left subtree and the right subtree of the root node 29. But however, we can't just stop there. So if you guys actually look at the implementation of identifying imbalances, we don't stop at the first node where we find the imbalance. We have to dig to the bottom and see like the very origin of where this imbalance comes from. So we then go to 15 and we check the imbalance, right? There is an imbalance there as well, because the height of the left subtree is 2, while the height of the right subtree is 1, 2, 3, 4, 4. So the difference is 2. So once again, it's imbalanced. Now let's look at 20. Is there an imbalance there? There actually isn't an imbalance in 20, because the left subtree is 3, has a height of 3, while the right subtree has a height of 2. So there is no imbalance there. So we have concluded that the imbalance is at 15. And as such, we have to do some sort of rotation upon the node of 15 so that we can get the tree back to its balanced position. Yeah. So, oh yeah. Alright, if you guys can't see, there's like this thing at the bottom, right? So, we basically have to fill the blanks, because this is a really easy way to remember what type of combinations you need. Because low-key it's kind of hard to remember, right? You have rotate left and right, rotate right and left. And you have to, you have to really know which of these combinations of rotations to use in which type of situation. So this is like a really easy way to do it. So the inserted node 18 is in the, so 18 is here, right? Which is in the right subtree of 15, which is the node with the imbalance. So is within the right subtrees. And what child is it in? Right? So this is the right subtree, right? Is 18 on the left or the right? Well, 18 is on the left of this right subtree. So 18 belongs here. So to fill the blanks, the sentence would then become, the inserted node 18 is within the right subtrees, left child of the imbalanced node 15. And just by semantics of English, like it's just a coincidence that this order, right, left, is actually the order of rotations that we have to perform. The next slide. Yeah, so it's within the right subtree's left child of the imbalanced node. So as you can see, it's right and then that's left, and yeah. Yeah, so this is the right-left case. And the solution of this is, coincidentally and luckily, we have to rotate right first. So we first rotate this to the right, and then we rotate left. And visually, what this looks like is, it's kind of hard to do visually, but you take this big chunk of the tree, right? And then you imagine turning it right. And then once you turn it right, then you turn this left. Now the turning this right part is like Okay, it's kind of weird to think about how it works, but let's just focusing on the turning left part. So what we know, like just by looking at it, is that this part is very small, and this part is very bulky, right? And that's kind of like imbalanced, because we want both parts to be either bulky or small. We don't want, we don't want to imbalance. So the second operation, rotate left, I think makes a lot of sense, because there's more on the right that's on the left, right? So we want to rotate it to the left so that there's more bulk on the left side, and then it can be balanced. So that's kind of how it works. But of course, rotate right needs to be done because we need to do some sort of rebalancing before we do that. But yeah, right now I think it would probably just be best to just memorize the order, because you know the implementation already, right? So yeah, so we first rotate right 20, and that's what's gonna happen. So 20 gets rotated to the right, and then the next one. Once we do that, then we rotate the left of, we rotate the node 15 to the left, so that we can redistribute some of this bulk to the left. So once we do that, as you can see, so some of this bulk is transferred to the left, and that's really how the rotation occurs. And now if you look at the tree, it's actually imbalanced, because for every node of the tree, the height of the left subtree and the right subtree has no greater difference than 1. And yeah, as you can see, now the tree is balanced. And that's basically the part of binary search trees. But you guys want me to go through the code? I do have like a segment of the code available, like a little bit. Wait, hands up who wants to see the code, kind of. Alright, that's chill then. Alright, you guys are smart then. Alright. Yeah, so now Andrew is going to go through the rest of COMP2521. That's like graphs and stuff. But yeah.
Okay, thank you, Eric, for going through trees. So we still have more topics to go through. Just by the way, I'll probably go through graphs, and then we'll probably take a break somewhere in graphs or after I finish graphs. Might be a bit hard, but we'll see. Okay, so firstly, to talk about graphs, if you look at diagram A, this is probably how you imagine a graph, but this isn't a really good way to do it in code. Like when I first thought of graphs, I was thinking, okay, what if it was like a linked list, but every node had multiple neighbors, I guess. But then the problem with that is you would have infinitely, every node would have to have different amounts of things, and your struct wouldn't be good. So the two main ones we'll look at is firstly adjacency list and an adjacency matrix. So with an adjacency list, I imagine it as an array of pointers, and I know an array is just a pointer as well, but you imagine it as an array of pointers. So for, let's say, node 1, if it's next to node 2 and node 4, that means it has an edge between, right? What we're going to do is insert in the linked list that starts at 1 in the array, either 2 or 4, and in this case both. And for 2, we would insert 5. For 3, we can insert 6 and 5. So essentially what we do is when we want to represent an edge, we insert it into the linked list starting at that array index. Okay, and then we have our other representation, which is an adjacency matrix. So within an adjacency matrix, this is sort of a simplified one for an unweighted graph. What we do is essentially we have this matrix of zeros and ones, and if there is an edge between two nodes, we place hold on, it's fine, don't move it. If there is an edge, we place a 1. If there is no edge, we place a 0. How does this work? Well, we have essentially in the column indexes along the top and the row indexes on the left, and let's say we have some entry aij, so just one of the entries. If there is an edge between node I and node j, we would put 1 there at aij. That's basically how an adjacency matrix works. Yeah, that should be pretty. You should know that by now, hopefully. Yeah. The next thing we're gonna go through is the two main graph traversals, which is BFS and DFS. So the way I think about BFS is we sort of explore the graph in like levels. So like we start like from one node, we visit its neighbors, and then the neighbors of that next level, and so on. So we concept, yeah, move to the next level of neighbors. Now for the actual algorithm, the steps we have is we need a bit of machinery here. We need a queue. Yeah, so what we're going to do is onqueue the starting node. Okay, yeah, thanks. We're going to onqueue the starting node, and then we dequeue it, we process it, we'll get deep into that, and then we onqueue its unvisited neighbors. So one other thing we will need for both BFS and DFS actually is a visited array, and all this says is true if we have visited it and false if we haven't. And then we repeat until the queue is empty. Okay, so yeah, the data structures we need are queue, a visited array, and also a predecessor array. So we need this predecessor array to store the path. Now, it's technically optional, but like for something where we want to find the shortest path in a unweighted graph, we may use EFS, and one thing we would need to do is to reconstruct the shortest path perhaps, and for that you need to iterate through the predecessor array. But if you don't need to do that, it's technically optional. And oh yeah, okay, you can click on that. It's just a GIF. Just open it.
It's actually both.
Like that goes through how it works, and you can see it does go by level. Yeah. The next thing, I wouldn't focus too much on like exactly each step in the BFS at this stage. I think the high level is probably more important. And then DFS. So DFS is kind of, we want to, let's say that we have paths in a maze. The idea behind DFS is we go to the end of the path. If there's nothing there, we go back to some splitting point or some start point, and then we go down another path and we go to the end. So the point is, how it's different from BFS is that we go to the end. We go as deep as possible. So the steps of this algorithm is we need to push the starting node onto the stack. Now we can explicitly use stack, or we can use the core stack. And then we pop a node, we process it, so do whatever we want to it, and push its unvisited neighbors. And we repeat until the stack is empty. So you can see it mirrors BFS very closely, except instead of a stack, we use a queue. Yeah, so the data structures we need are a stack, a visited array, and a predecessor array. You can show the GIF, but I think you might have done this in like Lab 6 or something, where you like code up BFS, code up DFS, and there was like a visualizer. You're probably pretty familiar with that at this point, hopefully. Yeah, so the time complexity of these, both of these are linear. So O of V, which is the number of vertices, and E plus E, the number of edges. And the reason this is, well, each vertex is onqueued and dequeued once, right? Because we need to visit every single vertex, because like we're BFSing through it, right? And this results in OV operations. And then we also, if you remember, for each node, we want to look at each edge on the node to see its neighbors, right? And what this results in is another O of E operations. Now you might be concerned that, okay, each edge, it could be connected to more than one node, and therefore we consider multiple times. And yes, that's true. It will be considered at most twice. Actually, it will always be considered twice, because an edge can only connect two nodes, right? So it will be considered from each node once. But this is fine. This is just O of 2 times E, is still O of E. Next. Okay. DFS is, because these algorithms are so similar, the type of complexity is still the same, over V plus E, and the reasoning is very, very similar. So each vertex is pushed and popped from the stack instead, or recursively called once, resulting in O of V operations, right? Because we still need to consider every vertex, just like in DFS. And then each edge is considered once for each of its endpoints, resulting in O of 2E, but still O of V operations. And this is fine, resulting in O of V plus E. Okay, yeah, let's look at a problem. Strongly connected components. So, what is a strongly connected component? It's a part of a graph where we can visit, from every node, we can visit every other node in that component of the graph, in that part of the graph. And we want to determine if the graph is strongly connected or not. So let's have a think about it. How would you approach this problem using DFS or DFS? It's fine if you can't think of it on the spot. It's probably, yeah, this is probably a harder question, maybe. But here's a solution. We want to perform a DFS from any node. If any node is not reachable, the graph is not strongly connected, right? Because the DFS reaches every single node, right? It needs to reach every single node, and if it doesn't reach any, like, if in your visited array something is unvisited, then the graph is not strongly connected. Now, this does result in a problem, which is, okay, what if, like, I started from somewhere that just so happened to be, like, a source node. Like, for example, imagine I had a node here and had an outgoing thing, right? That's all it had. But then, like, we had another node here that couldn't go to that one. That's a problem that this doesn't fix. So we need to reverse the direction of all the edges and then perform a DFS from the same starting node on the reverse graph. And then the same thing. If all nodes are reachable in both the original and reverse graph, the graph is strongly connected. This is just an example of, like, to motivate why we need DFS or DFS, right? Specifically, like, well, you might think, if I just want to go for a graph, they're basically the same, but they are different and they do get used for different purposes. The next thing we want to talk about is Dijkstra's. I think that's spelled wrong. I don't know.
No, that's fine.
It's fine? Yeah, okay. So, Dijkstra's is a single source shortest path algorithm that finds the shortest path from a source node to all nodes. And this is the only one you'll look at, really. So that's what it does. So it finds the shortest path from one node to all other nodes. Dijkstra's algorithm can be used in both a directed and undirected graph. Well, we only need to prove that it works in a directed graph, because if you think about it, undirected graph is just a directed graph, except we can add the edges going back in the other direction as well. Dijkstra's algorithm will not work if the edge weight is negative. You don't need to know why, you just need to know this. But I don't think they'll give you any, like, graph in the exam with a negatively weighted edge. So there will also be some machinery we need to use to complete Dijkstra's. Yeah. So we need a distance array, and all the distance array is the distance between the best known path from the source node to the current node. The array is initially all initialized to infinity because we haven't explored any of the nodes, so we don't know how far away they are. We assume the worst case, which is that they are infinitely far away. And also accept the source node because, like, we're already there, so we can just say that's an array of 0. Distance is 0. And then we also need a predecessor array. So this array keeps track of the node where we came from to reach the current node. Pretty self-explanatory. Yeah. And when we say where it came from, we mean directly, so directly before. Yeah. Okay, so we have those two pieces of machinery. This is the actual algorithm. So we want to maintain a set S of vertices for which the shortest pathway has been found. This will be initially empty because we haven't found anything. This is often a Boolean array. And then for every vertex V, maintain a value dv, which is the weight of the shortest known path from S to V. That is the shortest using only intermediate vertices in S. Initially, ds is 0 and dv is infinity. for vertices. At each stage, we add to this set the vertex v, which is in the total vertex set of the entire graph. That's also not in S, it's just some mathematical symbol, but that's all it means. So it's not in S, but it is in V, so it's just something that's not in S, which has the smallest dv value. Record this value as the length of the shortest path from S to V, and update other dv values as necessary. And this is the actual code itself. So this is, I guess it's pseudocode, but you get what I mean. We take in a graph G, we assume it's already created. We have a source vertex as well, and then we need to create a distance array, initialize everything to infinity, create a predecessor array, initialize to -1. The only reason we initialize, you could initialize it to like any negative number, I guess, is because we're probably indexing our nodes from 0 to n minus 1, right? So we want to initially set the predecessor to something that can't be, that doesn't exist yet, basically. And then we want to create the vertex set containing all the vertices of G. And then we also want to set, as we said, the distance of the source node to 0 because we're already there. So we set everything to infinity before. So while this vertex set is not empty, we want to find vertex v in the set such that this v is minimal. And we want to remove v from the set, and then for each edge from v to some other node w, in G, we want to relax along. And what does it mean to relax? I'll go to the next slide. Okay, that's fine. What does it mean to relax? Well, essentially all it is we have some current shortest node path, right? You can go to the next slide, by the way. We have some current shortest node path. But now we're looking at this new node. For example, let's say the shortest node path from A to D is 30, yeah? And then now we're looking from B and looking at all the outgoing edges from B. Well, we know that the distance to B is 1, the shortest distance to B is 1, and we look at this new edge B to D, we know that this distance is 1. So we know that the shortest distance from A to D should now be from A to B, then B to D, right? Instead of going straight from A to D. Because this reduces the distance from 3 to 2. And all relaxing is saying is the new dist of A to D is now, the new dist of D is now going to be dist of B plus the edge weight along B to D. Does that make sense? Yeah, I hope that makes sense. So for Dijkstra's algorithm, in the worst case scenario, we have to visit every single node and traverse every single edge to find the shortest path. And for each edge traversal, we may also have to add the new into the min heap. Now, we'll talk about heaps later, but I hope you have some idea. All the heap is to do is to maintain a priority queue. And the reason we need this priority queue is because if you remember from before, we needed to look at the minimum weight edge each time.
Oh yeah.
Yeah, like we need to look at the minimum weight one first. And to do that, we need to create a priority queue to prioritize looking at the minimum ones first. Now, the time complexity of a heap or a PQ using a heap is going to be log v for each insertion, and deletion as well, actually. And so traversing all the edges is simply e times log v, because we have to do it for each edge. And for each node to access from the min heap, this also takes log v, so the total time complexity to access all the nodes is v log v for this, and all of e plus v log v total. Yeah. So, we don't need to look at this, but you can do better, but it doesn't really matter for us. Yeah. Next up, we're gonna look at some MST algorithms. The first one, and probably the most important one, the one that everyone uses actually, is Kruskal's. So, we're gonna firstly, okay, I guess what is a minimum spanning tree of a connected graph G? Is a subgraph of G. So it has to have the same set of vertices, but it doesn't have to have the same set of edges. It needs to minimize the total edge length. So, and it does have to be connected, because otherwise, like, yeah. And what is Kruskal's algorithm? So we take all of the edges of the graph, and we sort the edges E in increasing order by weight. And edge E is added if its inclusion does not introduce a cycle in the graph constructed thus far. The reason this is, well, it's in the name, right? MST, we need it to be a tree. So if it forms a cycle, then we no longer have tree, so this is not good, so we don't want to do it. Yeah, so in the graph constructed, so thus far, or discarded otherwise. The process terminates when the forest is connected, i.e. when n-1 edges have been added. This point here, the reason this is like, it's like a mathematical point, I guess. If I have like a graph, like imagine I just had like 3 nodes. I had 1, 2, 3 nodes. How many edges would I need to connect these 3 nodes? 2, right? I only need 2. And if I had any more, well, because we're assuming that the edges have like positive weight, if I had any more, like I would only be adding weight to it, so this edge is completely useless to me, and will also form a cycle. Okay, to check whether an added edge belongs to a cycle, there's 2 ways we can do it. The naive way, which is we perform a DFS traversal through the graph, right? Because we know about DFS cycle check, right? Yeah? Yeah, okay. So we can use DFS, and then this results in a time complexity of E log E plus EV. This is not very good, but I think this is all you need, actually, for this course. But there is better, like if you use another data structure, you can do better in your E. The other one is Prim's algorithm. This is the other MST algorithm. Prim's is like kind of shit, I'm not gonna lie. Like nobody uses it, but what you do is you select an arbitrary vertex. We look at like the edges connecting to this initial vertex. And by the way, this initial vertex will say is in like some set S of like vertices which are within the MST. So we take this minimum weighted edge. So what we do is we look at all the edges connecting it to the other nodes, and we look at the minimum weighted edge. Now, I'm not gonna like mathematically prove that this results in MST, but it does. You probably will do that in like 3121 instead. We take the minimum weighted edge, and then in this case it's 4 to 1, and then we keep going. So in this case, when we had 0 and 1, right, in our selected MST nodes, right, the edges we had to the other nodes were 8, 11, and 8, respectively. Now, you could pick the other one as well, it doesn't actually matter. Like the other 8 from 1 to 2, but we picked from 0 to 7. So we want to pick the minimum one. And then we just repeat this over and over again, and this does give us an MST. And this is what it would finally be. Yeah. So yeah, we can, as you can see, like we can result in alternative MSTs. So like one graph can have multiple MSTs, and this is the case where we took 1 to 2 instead, because it was the same way as 0 to 7. Let's see how we're going behind here. Yeah, we might take a break right now. So yeah, we do have time, so we're gonna go through like an application of like the MST, I guess. And we'll ask this question: you've been tasked with powering the electricity network of, I guess it's meant to be Alabama. Given the locations of the town and the sole power plant, you are to construct power lines to ensure that all towns are connected to the power plant, and you incur the minimum cost possible, assuming that the cost of constructing a power line is proportional to its length. So in this case, I guess the MST has been kind of disguised, but you can see that the first condition aligns with the fact that the MST has to contain all nodes, right? If you imagine each town as nodes and electricity-wise as edges. And then the second condition is, well, I guess what makes the MST and MST is that the total cost, you incur the minimum cost, right? So we find the minimum spanning tree. Yeah. So what we kind of need to do is we have this like struct place, which is actually our, what would it be equivalent to? Our node, right? And we have the struct power line, which is equivalent to our edge. And then you just have this plan grid function, which is in reality just probably going to be an MST implementation. Okay. So we need this visited array, of course. Then we're going to keep track of the number of edges in our MST, right? Because remember, once we reach n-1, this is when we want to stop. Because this is where adding any more edges will do us no good. So while the total edges is less than the number of cities, and this enforces the n-1 because the number of cities will be n, and while it's less than n or n-1 and below, we want to keep going. So we're going to call our current edge, like we're going to define our current edge, and if the path already exists, right, we're going to insert this edge into our like power grid, right, into essentially the MST portion. Does that make sense? And then we have place 1 and place 2. Please, can you continue on the next slide? Oh, that's kind of annoying. Can you make it not 1? Yeah. Oh, that's fine. It's fine, it's fine. And then we're going to call this installed line. And then, like power lines, this total edges, okay, this is just notation. But what this does is we say that in stored line, we're going to put in the power lines, and then we're going to increment total edges afterwards. So this is like a postcrement, but it's just C++ notation. And then what we're going to do is reset the visited array for the next iteration, and then we continue essentially. That's kind of the whole algorithm that's encoded. Yeah, I'm going to so you can see how like that's actually just the MST algorithm hidden in a question. I think in your exam you'll get like a mix of like very direct things, like it would just say find like the height of a tree or something very directly. Okay, it's clearly a tree, but you may also get questions that where you have like this like question stem. You have to get through all the bullshit and find out what you actually have to do, right? Okay. The next thing we're going to look at is hash maps. So what is our motivation for hash maps? Well, consider the average case time complexity of array operations. If we want to search, it's O of n. If we want to insert delete, it's O of n. The reason this is, right, is if we insert or delete not at the back, so anywhere that's not at the back, in the middle, at the front, we have to shift the other elements to open or close the gaps, right? So question is, can we do better? We can, and the idea is if we give each element a fixed position in the array, then when we insert that element, we don't need to move other elements around, right? So we fix a position for an element, and when we insert or delete, we don't need to move other things around. This allows us to have O1 insertion. This is kind of what we want, right? So to do this, we need a hashing function. So a hashing function gives us this fixed position within an array. So here's an example. We have this hashing function, which is just element squared mod n, mod the size. And let's see what happens when we try to insert. So let's insert into an array of size 8 using this hash function. So in this case, n is 8, and now we call this array a hash table. Consider 10, 12, and 13. Yeah, so 10 squared mod 8 is 4, 12 squared mod 8 is 0, 13 squared mod 8 is 1. And that's the corresponding index, which is our fixed position that we're going to insert to. So, yeah, can anyone give me something to insert? Just any number. Sorry? 21? Yeah, sure, 21. Okay, let's see my math. Okay. 21, what we first do to it is we square it, so we get 441. And then we mod n, which is 8, which would be 1. Mod 8 is 1 because 440 is divisible by 8. And then we would insert into 1. Okay, now this is a bit of a problem because we already have 13 here, right? Right? We already have 13 in position 1. Can we have 13 and 21 in the same position? There are a couple of things we could do. We could just overwrite 13, but this is an example of what we call a hash collision. Essentially, our hash function, we map multiple things to the same index, and this causes a hash collision. We have a couple of strategies which we're going to talk about in a second to deal with these, and they are linear probing and separate chaining. So, as you can see, perfect, your first example gave us a hash collision. What will we do? We have separate chaining, linear probing, and then we also have double hashing. Yeah. So separate chaining. I think this idea is pretty intuitive. Is instead of like at that index having just a value there, let's say we have like the starter, like a linked list node. Essentially, each array position has a linked list node. It's kind of like the edge adjacency list from graphs. Basically, it's the same. It's like the same structure, I suppose. And then when we run into a hash collision, so for example, like the at index 1 with whatever it was and 21, we essentially insert 21 onto the end of the linked list at that array position. Yeah, and that's what we get. So if the problem is if all elements hash to a single slot, in the worst case, we'll have a O of n search. Because if everything maps to like 1, well, we just have a linked list at 1. That's not very helpful. We wanted to, what was our original goal? To get O of 1 insertion and deletion, right? And now, once again, we have O of n, because to search for it, or to delete it, or to insert it, we'll have to go through the linked list, and this is just O of n. What we can do is we can dynamically resize the underlying array when the total number of elements inserted is greater than the size of the array. So imagine my, in this case, this array is size 9, right? Once I've inserted 9 elements, I'm going to increase the size of the array. And basically what this does is, like, if we look at our previous hashing function, like let's say it was size 9, I'm modding by 9, so I have like 9 slots to insert into. If I increase it, I have more slots to increase it, like to put values into. So like because if I have like a uniform distribution of inserted numbers, then it'll be like pretty evenly distributed, right? So this assumes that we have a hashing function that distributes evenly. The next strategy we have is linear probing. So what we do is, firstly, if the load factor exceeds threshold, dynamically resize. By the way, what's the load factor? Load factor is just the percentage of the array we have used up, essentially. Yeah, so we hash whatever we hash to find our key, and if a collision occurs, when the next empty slot, we put our value in the next empty slot. So for example, if I were to just insert 22, and my hash function in this case is k%10, so if I inserted 22, it would just go into 2. No problems there. That's the same as like just inserting it, right? But once again, if we run into our problem with a collision, you see we already have 24 at 4. If we insert 14, right? Well, now we have to put it at index 4. Like we kind of do this lazy thing is like, okay, we'll just put it at the next thing. But in this case, the next thing already has another thing in it. It has 5 in it. So then we, once again, just say we're going to put it in the next thing. So we just put it in 6. That's the idea behind linear programming. So this does present a couple problems, but we'll get to them. Yeah, for lookup, it's the same thing as insertion, right? We just want to follow essentially the same algorithm we went through when we inserted it. What we want to do is, let's say we're trying to search for 14, which is inserted here. We first apply the hashing function to what we're searching for. We get 4. We see that 24 is here, but the thing is 24 isn't 14, but we know we put it somewhere else, like possibly, right? We keep going. We say 5 is still not 14, but once we get to 6, we say, okay, we found 14, we're good. Yeah, and this is where some of the problems arise. When we delete in linear programming, we have like these 2 main methods. One is the tombstone method, and the second is the batch method. So what the tombstone method does is when we delete it, we leave behind the tombstone. And well, what is the motivation for this? Well, if you go back to the previous slide, one more. Imagine we deleted 5. Imagine we deleted 24 actually, right? If we deleted 24 and we didn't like leave a tombstone or anything, we did nothing about it. When we try to find 14, what we find is that 4 is empty. Well, if 4 is empty, well, I guess the 14 just doesn't exist. But is that true? We already inserted 14, it does exist here. We deleted 24, there's nothing here anymore. And this presents a problem. We can't find some of the things in our hash map. It makes it kind of useless. So we have this new strategy. Instead of when we delete something, we make it no item or like empty, we leave behind a tombstone, like possibly -1 if your array is like only positive integers or some marker essentially. And what this allows us to say is that let's say we're searching for 4, right? Even if we deleted 24 or here we deleted 14, right? Even if this happens, we say you keep searching until I don't find a number or I don't find a tombstone. So I actually find something that's empty. Or I find the actual number, right, that I'm looking for. And this avoids the problem, because then if I were to delete 14 here, even though 4 is past it, I leave behind this tombstone, I say, okay, I'll keep searching because I may have placed more things afterwards. And then you can find 4. Now we've gotten rid of the problem of losing things that we placed in. The next method is the batch method, and it's kind of like, I would say it's pretty intuitive as well. So imagine we remove 24. What we do is now we reinsert 5, we reinsert 14, and we reinsert everything else along the list, right? Because then what this does is now this empty slot exists because of 24, but if we reinsert like 14, if we reinsert 5 here, that's fine. If we reinsert 14, we now move it to the place where it should be, so there are no gaps once again, right? And we keep doing this for everything that was before. That's basically the idea of the batch thing. Yeah, this continues because with 4 we want to reinsert it as well, and 18, because it's on that same chain, we want to reinsert it as well. Wait. Oh yeah. Talk about like some issues with linear programming is firstly clustering. You can imagine if we had a hash function that, like, let's say it didn't even just map things closer, like always to 4. imagine it map things to 4, 5, 6, 7, 8 a lot, right? Then we have this big long chain of items which when we probe for, right, we have to look through each one, and once again this ends up being like a linked list. This is once again O of n, this is bad. So we have long filled sections which can slow down insertion and lookup, like the exact type complexity and math behind it gets probably too complicated, but you just need to be aware that this issue exists. And then our final strategy is double hashing. This strategy, what we do is when we initially hashed it, okay, we got one thing, but maybe it's the same thing as another thing, like the same, it gives you the same key as another value. So my idea is, okay, let's define a new function, and let's just hash it again. So suppose our primary hashing function h1 of k is k mod 7, and we call our secondary hashing function h2 of k, which is k mod 3 plus 1. Let us try to insert 22. So when we insert 22, we first use our initial hashing function, which is k mod 7. This gives us a value of 1. Okay, 15 is already here, so that's a problem. Now what we do is we take 20, so we need to find a new place to put it essentially. What we now do is we repeatedly use h2 of k. So 20, so we had 22, now we mod 3, that gives me like 1 plus 1, which is like 2, I suppose. Wait.
22 mod 3 is 1.
22 mod 3 is 1. Yeah, but plus 1.
Oh, okay.
Yeah, which gives me 2. And what this 2 does is we say, we'll start from where we originally were, and we'll keep jumping 2 until we find a empty slot, essentially, and we can put it there. And you can see that actually linear probing is actually a subset of double hashing, I suppose, where it's like you jump by 1, but instead this time we jump by n. So what this, yeah, so to look up, we also resize if necessary, just because we don't want our array space to be too small, because once again we run into like, clustering and like everything being in one spot, which drives us towards O of n, which is bad. So for lookup, we also want to follow the same formula as before when we inserted it. So we apply the initial hash, and whilst the key/empty slot is not found, right, we keep jumping by the second hash increment. Finally, we have deletion. Backshift method for this is kind of way harder because of the varying increments. So you could imagine to backshift something, you may have to backshift everything by 2, backshift everything by 3, backshift everything by some value k. But the tombstone method is still the same. So we still get the same problems, right? Because remember, this is essentially just linear probing. We still get the same problems. If I delete something, I can't find the things after it. And then summary. Okay, yeah. So for deletion, all methods have O of 1 amortized time. So what we mean by amortized is sort of an average. Like if I did n operations, on average, everything would take O of 1 time. So the thing is, like, if you do a single operation, it could have O of n worst case, even assuming a good hash function and appropriate resizing. And the reason this is like, you could have, your hash could lead you like to one of those cases, like even if you do everything possible to try and prevent it, your hash could still lead you to one of those cases where either we're clustered in the linear probing and the double hashing, or we have like this linked list in our separate chain. But the thing is, this is just for one. Like if we do it for a bunch of them, it's very unlikely, given that our hash function is pretty decent, that like everything still ends up in one place. It's just pretty unlikely. So usually it's like O of 1 amortized. And when we resize by double. There's some like math behind it. but you don't need to worry about it. You may have done it in your assignment one as well, but I'm not sure actually. The final thing we're going to look at is like heaps and PQs. So heaps are a tree-based data structure, and they satisfy the heap property. What is the heap property? Well, it depends. We have two types of heaps, a max heap and a min heap. So in a max heap, the value in each node is greater than or equal to the value in its children. Yeah, when we say children, we mean like direct things below it. And in a min heap, the value in each node is the opposite, less than or equal to the value in its children. And then finally, we also have a very important thing which is called the completeness property. And this is that all levels of the tree except the last must be filled. The completeness property allows us to represent heaps with arrays. Okay, what do we mean by this? When I have a heap, what I need to do is I essentially need to put things in order. So if I were to put something here, I would put it here first, then here, then here, then here, then here, then here, then here. So top down, left to right. Okay? So it's not like a binary search tree where I can just insert things based on if it's exactly based on if it's smaller or larger to the left and to the right, because that will result in, if you remember, the binary search tree did not follow this completeness property. And this completeness property is really important. It also allows us to represent heaps with arrays, and we'll get to that more too. Yeah, just click right a bunch of times. Okay, so for an item at index I in the array, which is also a representation of a heap, the left child will be at 2i, and the right child will be 2i plus 1, and the parent will be at floor of I on 2. Now, let's have a look at why this works. And one thing we need to do to make it work is for 0 to be not included. So I guess we kind of waste this one spot, but it doesn't really matter, it's just one spot. We don't need to include 0, and the reason this is because it kind of breaks this thing, right? Where the left child is at 2i. Well, the left child, if I applied this to 0, this would give me that the left child is itself. Clearly wrong. But let's have a look at 20. Let's start at 20. So the left child of index 1, which is the root node in this case, is at 2, correct? Right child is at 2 plus 1, also correct, and you can keep going for that. Let's look at the parent. The parent of, let's say, 1 should be at I on 2 and root floor of that. So it's in position 5 in the array. 5 divided by 2 is 3.5, floor of that is 2, and you can see that 17 at index 2 is the parent. Yeah, this works, it's very nice. I guess you could like just think about it more to get a better intuition for it, but it just, or you could just take it at face value and it just works. So for insertion, what we do is we add item at next position on the bottom level. But the problem is this may violate the heap property, right? Because if we just put it at the bottom right, let's say we have a max heap, like it could be bigger than the parent, or like the vice versa for a min heap. And what we have to do is we have to do this fix up operation. So that is, while the item is greater than its parent, swap with its parent, also make sure it's not at the root. Because if we like swap it, if it's at the root already, then you know it's already like the biggest or the smallest. And if we try to swap it with something above it, there's nothing above it. So for example, we insert 26. 26 is greater than 11. We swap those two. Next. And then 26 is also greater than 20. We swap those two once again. Okay, 26 is now the root, so we swap. And you can see that this allows us to, you can see the heap property is still maintained, right? We could also go through the math behind it, but there's like, you don't need to know it really. But you can see like, if this is bigger than this and I swap it with that, it will still be bigger than the other thing. That's basically the math that solidifies it, but you can just remember this. And then for deletion, this is also a bit more complicated than like just deleting from a binary tree, for example. the problem is, like, let's say, imagine we deleted the root. Okay, now we just have nothing to connect everything to. We've lost the rest of our tree, essentially. It's like somewhere in memory, we don't know where it is. Not good. So what we're going to do is we replace the root item with the last item. Because remember, when we delete from a heap, right, we delete from the top. So first we swap them around with the last item, and the last item is the item the furthest bottom level, most towards the right. And now, the problem is the heap property may be violated, so we must fix that. Yeah, swap this. So imagine we want to delete 20. We go left. So what we do is we swap 20 with 8, and then we delete it. So now 8 is the root node, right? But the problem is, you can see that 17 and 11 are great. So we need to fix down. So this is kind of the opposite of fixing up. So that is, while the item is less than its greatest child, we swap it. So we see the greatest child of 8 was 17, we swap those two. The greatest child of 8 is 13, and we swap those two. And once again, there's like some math to solidify that this does in fact, for sure, maintain the heap property, but all you need to do is really just remember that this is the process we go by. And very closely linked with heaps, and probably the main use for heaps, is to maintain priority queues. So for example, you might use a priority queue, like you need to use a priority queue in Dijkstra's. That's like one place where you might need to use it, although I think they'll probably just give you like an ADT for it, so you don't have to worry too much about it if you are asked to implement Dijkstra's. So priority queues are data structures. It's probably incorrect to say it's data structure, probably a ADT, abstract data type. Operate similarly to regular queues in that they're first in, like regular queues which are first in, first out. Here it's not quite, but it's still sort of the thing at the front is taken off first. So each item has an associated priority. And the priority determines where we want to put the item, I suppose. So we onqueue from the back, we dequeue from the front. So the element with the highest priority needs to be at the front. So we have a few operations for PQ. So the first one is the peek, is essentially we look at the front, like the front of the queue, we get the item with the highest priority. That's it. We have deletion. So what we do is delete and sometimes return the item with the highest priority. Like, you can always just implement it with returning it, and you can just not use it if you want. And then for insertion, we add an element to the queue with a given priority. So what this requires is that firstly we put it in, we consider it, and we want to put it into a position where the priority is greater than the last thing and bigger and smaller than the next thing. We want to put it in its correct place, given its priority, essentially. And then finally, just like a normal queue, we have is empty. So it just checks if the priority queue is empty. It's pretty, yeah. So P queues, like, are almost always implemented with heaps. That's why they're so closely related. But you can implement them with other data structures like an array, a DQ, or something like that. And you can see that heaps are most common. Why? Well, we didn't quite go through this before, but because of the completeness property, right? What do we know? That the heap has at most log n levels, where n is the total number of items in the heap. Since it's log n, if we need to fix up or fix down, we only need to fix up or fix down log n levels, which means that any operation, insertion and deletion, also is going to be log n, and the peek operation or the isEmpty operation, we just check the front, right? We just check the front, or like deletion, we just delete from the top element, right? The first thing. It's going to be O(1) for peek and isEmpty, and because even though delete, we're deleting from the top, remember we had to fix down the element we swapped with, so it's going to be fixing down log n levels. So we have insertion, which is log n, deletion, which is log n, and peak and is empty, which is all of 1. Yeah, that's it. I think we went through everything. Yeah.